Hey Tim, I thought we were done with trigonometry. Looks like there's more here. If we do a recap, pi radians was defined as 180 degrees, 2 pi, 360 degrees. So just remember that for cos and sine, your period is 360 degrees, but for tan, it was 180 degrees. And for a 90 degree triangle, sine x is opposite over hypotenuse, cos x is adjacent over hypotenuse, and tan x is opposite over adjacent. And from that you can see that tan x is simply sine x over cos x. Why is that? Well, you take that one, opposite over hypotenuse divided by adjacent over hypotenuse, and the hypotenuses cancel, and you're just left with opposite over adjacent, or sine over cos. Then we've got this rule, sine squared x plus cos squared x equals 1. This rule is used quite extensively in the section, so you need to know it. And from that, if we just move the cos squared x across to the other side of the equation, we get sine squared x equals 1 minus cos squared x, and cos squared x equals 1 minus sine squared x. So this is an important equation, and you need to know him quickly. Now we can introduce secant, cosecant, and cotangent. Secant is 1 over cos x, and cosecant or cosec is 1 over sine x. Note how they name these things. I would have called cosec 1 over cos, but no, because it's 1 over, it's like otherwise, so they've gone and said cosec is 1 over sine, and that's how you remember these things. Sec 1 over cos, cosec 1 over sine. Doesn't make sense, but that's how it is. And then cotangent is 1 over tan, which is just cos x over sine x. If we look at the shape of these graphs, I'm going to start with cosec x because I like sine. Okay, we all learned about a sine wave before we did this trigonometrical stuff. And so sine x is a sine wave. You see it in the sea all the time. So always reference everything with respect to sine x. If we have the graph y equals cosec x, sine x is 0 at x equals 0. So 1 over 0 is infinity. It's infinity positive if x is slightly positive, and it's infinity negative if x is small and slightly negative. And the sine of pi by 2, or 90 degrees, is 1. So 1 over 1 is just 1. You can see then how this graph starts high here, infinity, and comes down along that asymptote and intersects at 1 at 90 degrees, and then goes back up again. And you can see how the sec graph is just 90 degrees out of phase with the cosec graph, just like sine and cos are 90 degrees out of phase with each other. And so the graph is similar in shape, but just shifted. And then the cot x graph is 1 over tan, so it has exactly the same shape as the tan graph, but it's just shifted by 90 degrees. There are two important trigonometrical identities in this section, and we use sine squared plus cos squared equals 1 to derive these. In the first case, if we just divide by cos squared, so sine squared divided by cos squared gives you tan squared, and cos squared divided by cos squared gives you just 1, and that's equal to 1 over cos squared, which is sec squared. So there's your first equation. And the second one, we use the same sine squared plus cos squared equals 1, and we divide it by sine squared. So sine squared over sine squared is 1, cos squared over sine squared is cot squared, and 1 divided by sine squared is cosec squared. Although these are simple to derive, it's good to memorize them. It's good to know them and be able to spot them in the exam. If you see, for example, a cosec squared, ask yourself, how can I express this maybe with a cot squared, and vice versa. So be on the lookout for that. So here's a nice example. Show that 1 over sec x minus tan x equals sec x plus tan x. Ouch, looks tricky. But let's start off. We put the two equal to each other, and if we times out now by sec x minus tan x, we're going to be left with just 1 on the left hand side. And if we look there, we see there's a difference between two squares. We've got a sec plus tan times sec minus tan. Always be on the lookout for the difference between two squares, because you're not going to get a middle term. Hey? The middle terms cancel. And so you're going to be left with 1 on the left hand side and sec squared x minus tan squared x on the other side, on the right hand side. Now we apply our little rule, which says that 1 plus tan squared equals sec squared. And if you put 1 plus tan x into here, you'll see that 1 equals 1. And so we've proved our thing as requested. It's very important to recognize and use the difference between two squares. Always be aware of that. Here's another example. What's the square root of sec squared x minus 1? Well, if we use equation 1 to replace the sec squared x, there it is over there, we get 1 plus tan squared x. So 1 plus tan squared x minus 1 is simply tan squared x, and if you square root it, you're left with tan x. It's quite simple. What about tan x divided by 1 plus tan squared x? Immediately you recognize that you've got a tan squared x here, and you can put, you can replace that, well, you've got 1 plus tan squared x, which is sec squared x, so you've got a tan x over sec squared x, and then you'll see sec squared x is now a cos squared over sine squared. And yeah, so you can easily simplify these things. Look out for the tan squares and the cos squared, but also if you have to, then you break down the tan into sine over cos and the cot as cos over sine, as a sort of a continuation of that. Now we have the addition formula for sine and cos, where we say that sine of a plus b equals sine a cos b plus cos a sine b, and sine of a minus b is sine a cos b minus cos a sine b, and so it goes. Now these formulae need to be also memorized. We'll touch on how to prove them, but it's not really required, and the important thing is to be able to apply them in an exam situation. So how do you remember something like this? You can learn them all by rote, but it's much more important to spot patterns and remember them according to pattern. Now I like to use sine, so sine always comes first. So there you have sine a plus b, and so it's expressed as sine times a cos plus cos times a sine. You see the plus there? It ties in with that plus over there. If it's sine a minus b, the minus ties in with that minus over there. Now cos, he's like the second cousin of sine. So if he's a little bit otherwise, so cos a plus b, you're going to get a plus turns into a minus, minus into a plus. Then notice how the pattern goes. You always got an A and a B, A, B, A, B. So it's easy to write it down if you need to. Easy to memorize. And then finally, how do you get the coses and sines right? Well, sine of A plus B is just going to result in a sine wave, which is an odd function. You can see I've drawn a little graph here. There you've got your sine, starts at 0 and goes high, and goes down, and it goes negative. You see, it's an odd function. So, and cos, on the other hand, is an even function. So if you have sine times cos, you're going to get an odd function. Now here we want an odd function. So it's sine times cos plus cos times sine. And similarly with the sine a minus b, you have an odd function. So it's sine times cos minus cos times sine. Then for the coses, you want an even function. So cos times a cos is even, and a sine times a sine is also even. Okay, when you have two odds multiplied out, you're going to end up with an even function. And so it goes. So that's just how one memorizes this. So if you can peg the first one, sine of a plus b is a sine a cos b plus cos a sine b, and the rest will all follow if you apply those simple tricks to memorizing. How do these addition and subtraction functions get proved? Well, you don't need to know this, but it's nice to have an understanding. If we have a circle here, and we've got an angle B here and an angle A here, and I'm asked to show and find cos of A minus B, so we're going to prove this guy. We're going to prove this guy over here, cos of A minus B. So that angle there is A minus B. If we look at, let's take P. The coordinate of P, this radius here is 1. Okay, so we're spinning around at 1. That's 1, and that's also a radius of 1. So the coordinates of P is simply cos A. Okay, there's my angle A, talks to P. So the x coordinate of P is cos of A, and the y is sine of A. Why? Because cos of A is opposite, divided by 1, and cos of A is adjacent, divided by 1. Similarly, q is just cos b sine b. So if we look at pq squared, we use Pythagoras, we can say that pq squared equals this short length squared plus that length squared. But this short length squared is simply cos of b minus cos of a. You square the whole thing in brackets and multiply them out, and you do the same here. So this is sine a minus sine b squared. So you end up with a nice expression for pq squared. So now that we've got pq, we can, in terms of cos and sine of a and b, we can now look focusing on this triangle because they asked us about a minus b, cos of a minus b, and that's a minus b there. Now we know that this side is 1, this side is 1, and we've got an expression for PQ. And if we throw that all in and we use our cosine rule, remember it's not a 90-degree triangle anymore, then we can reduce the expression for cos of a minus b, and we can prove our rule. And once we have that, and once we've proved that cos of a, what cos of a minus b is, we can get cos of a plus b as well, because if you replace b by minus b, okay, then we use cos of minus b equals cos of b, because cos is an even function, and that's something that we learned in P1. And also that sine of minus b equals minus sine of b. And then to get the sine of a plus b, sine of a plus b equals cos of 90 minus a plus b. Remember how if you have, you can say that sine of 90 minus x equals cos of x, and vice versa. Okay, so that's another that 90 is like a complement, and you can then flip between sine and cos. Here are some examples applying the addition formula for sine and cos, and the key here is to look out for special angles. So if we asked for cos of 75, at first 75 looks impossible, because how do we know that, and we want the exact values. But cos of 75 is simply cos of 45 plus 30, and the special angles being 30 degrees, 45 degrees, and 60 degrees. So now it's easy to split this up using our addition formula for cos of a plus b. Just expand that, and then you can work out what the cos and sine of these special angles are, 45 and 30 degrees. And here's another similar example. Find the exact values for cos of 15. Well, cos of 15 is just 45 minus 30. Now we've got the cos of a minus b, and we can expand that and put in the exact values. This example says, show that sine of a plus b plus sine of a minus b equals 2 sine a cos b. Well, again, recognize that you've got additional formula here, and just expand them as per what you've learned. You expand them, you'll see that some of the terms cancel, and you're going to be left with sine a 2 times sine a cos b. Here's another example. Find tan x, given that sine of x plus 30 equals 2 cos x minus 30. When you look at these, at first glance, you think this is impossible. How do you go about this? There's no methodical approach. You just need to recognize that you've got a double angle here. So it's sine of a plus b, which you expand, and you've got 2 cos x minus 30. So you've got a cos of a minus b. You expand them both, and then you can substitute values for, you're going to end up with sine and cos of 30 degrees here. And that's quite simple because that's special angles again. And you reduce that into your equation, and you'll end up with something like this, where you've got an expression times sine x and an expression times cos x. What's nice here, you've got your sine x on one side and your cos x on the other side. So you can easily say, well, okay, let's divide by cos, and you've got tan. Now it's easy to find. So tan x equals some expression or just a number. And once you have tan x equals a number, you can find x. So these things always unravel, but you need to spot the fact that it's a cos or sine over a plus or minus b, and apply those formula. If you can just do that, if you can spot these things, that's half the job done. Then we've got addition formula for tan. So tan of a plus b equals tan a plus tan b over 1 minus tan a tan b. And similarly, tan a minus b equals tan a minus b over 1 plus tan a tan b. Again, how do you remember these things? Just remember that the sign, tan a plus b, the plus gets transferred to there, and then it's just whatever's up top there is the opposite on the bottom. Okay. Yeah, it takes a bit of application, but try and look for patterns rather than just remember everything by rote. Then we have the double angle formula, which are just derived from the addition formula. So if you have sine of 2a, it's the same as saying sine of a plus b, but now a equals b, so it's the sine of 2a. And you'll see how that formula that you have, the addition formula, reduces to 2a cos b. And then cos of 2a is equal to cos squared a minus sine squared a. Again, just a equals b. Just put them in the formula and play around with them, and you'll see how quickly they reduce to these expressions. And because cos squared a minus sine squared a equals 1 minus 2 sine squared a, so we've applied our rule of cos squared plus sine squared equals 1. Okay, so we have just that cos 2a equals 1 minus 2 sine squared a, and cos squared 2a, cos of 2a is also equal to 2 cos squared a minus 1. Just by applying that our basic rule here of sine squared x plus cos squared x is equal to 1. And then tan of 2a equals 2 tan a. See there? Tan a plus tan a is 2 tan a divided by 1 minus tan a times tan a, tan squared a. So it's quite easy to deduce these from the double angle formula. But it's also useful to know them because you haven't got time to be able to derive these things. I just want to play around a little bit with different forms of sine x. So here I've drawn y equals sine x. See there, he's got a period of 2 pi. Okay, he reaches 1 at 90 degrees, starts at 0. So what about y equals a plus sine bx? Here I've got an example, y equals 1 plus sine of 2x. First of all, you should notice that it's shifted by 1. So in other words, the midpoint of this guy is going around 1. So the difference here, it's the symmetry around 1. So you just need to, you can just shift him up by the value a. A could be positive or negative. If it's negative, you're going to find this graph will go under the y-axis there. So that's easy. Shifting it up and down is the constant term that's outside of the sine. But what about the sine 2x? What does that mean? Well, it means that when x is 180 degrees, you're going to be taking the sine of 2 times 180, 360 degrees. So you would have completed a full cycle within 180 degrees. So you can see here, within pi radians, 180 degrees, there you've got a full cycle already. So here's my original sine. He takes 360 degrees, whereas this guy, he's doubled up. That's quite interesting. When this number b increases, the sine wave goes faster, not slower. You'd think of a bigger number would take a longer time, but it's not. It's counterintuitive. So the bigger that number, the tighter your sine and cos graph is going to be. What about sine x minus c? We have a constant c, and we say, what is the sine of x minus c? Well, what do you expect? I would expect that the graph would go backwards when you minus a number, but that's not the case. It actually goes forward. All right. So whenever there's a minus, you must think of it as going to the right. So here I've drawn another little sine graph. There's the original graph. Okay, nice and easy, 360 degrees. And here we see how sine of x minus 60 moves it forward, moves to the right by 60 degrees. Okay, and it's almost like with remember when you find roots of polygons, you say x minus 2. Where do you think that root's going to be? Your first instinct is it's going to be at x equals minus 2, but it's not. When x is 2, that's where the naught is. Okay, so it says x minus 2, but the root is at 2. And it's obviously simple, but sometimes you just need to remember that it's counterintuitive. All right? I don't know if that's helpful, but anyway. So what about, here's a little bit more complicated now. What about y equals sine of bx minus c? Now, so we see we tightened it up. It's going faster, and it's also got a constant here. What I would suggest you do in a case like this is rather write it as sine of b times x minus c over b. Now you can see the whole thing is tightened up. And what is it shifted by? Well, it's shifted by c over b. Here's an example. You'll see when you do this guy, let's say we had used the 60 degrees. We'll see that because the graph is tighter now, it's not shifting it by 60 degrees. It's actually shifting it by 60 over 2. Okay, we had a 2 sorry. Here we had a sine of 2x. Okay, so it went faster, it went within 180 degrees. But if we have 2x minus 60, okay, it doesn't shift this tight graph by 60, it actually shifts it by 30 degrees, it's slightly less. And that's why we put this, rather put sine of b times x minus c over b. In this case it would have been 2 divided by, or rather 60 divided by 2, which gives you a 30 degrees. So let's just have a look at this. So here we've got another, here's our standard sine graph, and then here's the tight one here. This is the graph we're plotting, y equals sine bx minus c. And you can see how it's now shifted 30 degrees when we have sine 2x minus 60. That's using our previous example. So just remember that when you've got a coefficient in front of the x there, that your shifting is going to be not as much as it was. Okay. So just to give you a feeling for how these things work. Another rule that one needs to know, if you have an a sine x plus b cos x, it can be, if you plot those out, plot the sum of those two terms out, you're going to end up with a sine wave that's been shifted, and it's also got an amplification factor. So a sine x plus b cos x can be written as r sine x plus alpha. So r and alpha are two constants that you can easily find. And also a sine x minus b cos x equals r sine x times x minus alpha. Similarly, a cos x plus b sine x equals r cos x minus alpha. A cos x minus b sine x equals r cos x plus alpha. So again, these are rules that one needs to go into the exam, and you need to know them. And using what is r and what is a, these coefficients here. Well, r equals, call it the magnitude of a vector a and vector b. So r is just the square root of a squared plus b squared, and a equals r cos alpha, b equals r sine alpha, and alpha has to be an angle between 0 and 90 degrees, power by 2. And a and b are both positive. So if you keep this in mind, it's quite easy to express the sine x plus a cos x as a r sine x plus alpha, etc. So there's an example here. Express sine x minus 4 cos x in the form r sine x minus alpha. Okay, so we identify that a is 1, the coefficient of sine x is 1, and b is not minus 4, okay, because we said a and b must be positive. So we need to look and see, well, what form is it? Well, we've got, so it's a sine x minus b cos x, and then we can get it in this form r sine x minus alpha. So even though there's a minus there, just be careful. You must know that yeah, the negative is there, but b is positive. All right, that's b. Okay, so we conclude that a is 1, b is 4, and we can find that r equals just simply a squared plus b squared, the square root of it, which is the square root of 17, and then we say that a equals r cos alpha, and from there we can get that cos alpha equals 1 over square root of 17, because we know what r is, and we know what a is. A is 1. And so it follows quite easily. I think the hard part with these is just identifying in what the correct format is, and then just applying the equation. So here's a question: find the maximum value of 5 cos x plus 6 sin x. Well, the maximum value would just be to find r, because the coefficient of any sine and cos is going to be its maximum and minimum value. So if you can find R, you've got the magnitude. The alpha is just for the phase shifting. If we look at this, we see that, what is it? We've got A is 5 and B is 6. So they want it in the cos form. Okay, so there we have it. A cos x, it's 5 times cos x plus 6 times sin x is equal to R cos x minus alpha. And since A is 5, B is 6, you can easily find R. A squared plus B squared, take the square root. And there you have it. So, yeah, this chapter, there are some quite heavy proofs and that sort of thing, which I don't know. For me, the most important thing is to know the outcome of these proofs. It's good to have an understanding of them, but in an exam situation, you want to know these things and be able to recognize them. So, yeah, be familiar with them and be able to spot the different forms and be able to apply them. So, yeah, if you've got any questions, give me an email. I'm more than happy to help. And thanks for listening. Ciao.